Good day everyone, we are the group 3 and we will be discussing to you about the finite geometry. But before we start, we will be going to introduce to you ourselves.
I am Apple Grace and PENTON.
And I am ANDRIAN Saliot.
I am Angela Miguel Ye.
I am Maria Jasmine AÑASCO.
And I am ARLYN TAGHAP.
And here's our presentation.
When you think of finite, you always associate it with countable things. In Euclidean geometry, you deal with an infinitely many points, lines, and planes as well as bits of aggregate theorems that continue to grow. In this topic, you are dealing with geometry with few numbers of axioms, few theorems, and finite number of elements, which is called finite geometry. This type of geometry provides a rich opportunity from which to study geometric structure, as well as serve as an excellent springboard into discussion of other geometries like transformational and projective geometry. This will provides you with the concepts of the different finite geometries such as 3-point geometry, 4-point geometry, 4-line geometry, and 5-point geometry, and other types of finite geometries like Fanon's and Young's geometry. At the end of the lesson, students should be able to discuss the properties of finite geometries, identify the axioms for 3-point, 4-point, 4-line, and 5-point geometry, and prove their theorems, and prove the finite geometries of Fanon and Young.
Finite geometry started when mathematicians and geometers followed the axiomatic system in the late 1800s. It was developed while attempting to prove the properties of consistency, independence, and completeness of an axiomatic system. Geometers wanted models that fulfilled specific axioms. Often, the model found finitely many points, which contributed to the name of this branch of geometry. Finite geometry is any geometric system that has only finite number of points. Finite means limited or fixed.
3-point geometry. Axiom 1 there exists exactly 3 points. So the points is A, B, and C. Axiom 2, there 2 distinct points are on exactly one line. So exactly one A and B. Then axiom 3, not all points are on the same line. So A and C, B and C are the same line, and A and B are not the same line. Axiom 4, 2 distinct lines are on the last one in the common point. So 2 distinct points, A and B. Yeah. Theorem 1, any 2 distinct lines are exactly in one point. So 2 distinct lines, A and B, then that 3-point geometry has exactly 3 lines. So ang 3 lines ani is A and B, B and C, and E and C. Theorem 3, each line contains only 2 points. Mga 2 points. So next is 4-line geometry. There exists exactly 4 lines. So line B, C, F, F, E, D, line B, D, E, line C, D, A, they are the 4 lines. Axiom 2, any 2 distinct lines are intersect in one point. So line B, D, E, line A, D, C, so ang common point nila is D. Then axiom 3 is each point is on exactly 2 lines. So line A and F, F, C, D are the exactly 2 lines.
Now let us proceed to the 4-point geometry. In 4-point geometry, there are 3 axioms. The first axiom is there exists exactly 4 distinct points. So in 4-point geometry, there exists exactly 4 points. So these are the points, point A, point B, point C, and point D. And axiom 2, any 2 distinct points are on exactly one line. So in 4-point geometry, there are the 2 points has exactly one line. So let's say for example the point A and point D have a one line. So let's call it the line is line 1. And the point A and point B has exactly one line. So let's call it again and line 2. So these are the examples and point and axiom 2. The axiom 3, each line is on exactly 2 points. So the line are exactly in 2 points. So the line 1 is exactly in 2 points, the 2 points A and point D. Okay, the 5-point geometry. The 5-point geometry has 3 actions. The first action is there exists exactly 5 points. So let us count if it is true, if it is 5 points. So point A, point B, point C, point D, and point E. So it is true that the action 1 it has exactly 5 points. And the action 2, any 2 distinct points have exactly one line in both of them. Any 2 distinct points have exactly one line in both of them. So each point has exactly one line in both of them. So the point A and point D has a one line, and point A and point B has a one line, same as others. So the action 3, each line has exactly 2 points. So the action 2 and action 3 is vice versa. No, action 3, each line has exactly 2 points, so each line has exactly 2 points. The point A and point B has a line, and point B and point C has a one line. So that will be all.
Okay, so let's proceed to the finite geometry of Fano. So Gino Fano, 1871-1952. He was born on January 5, 1871 in Mantua, Italy. So he was credited with being the first person to explore finite geometries beginning in 1892. And he is best known as the founder of finite geometry. So his work in this new geometry included 15 points, 35 lines, and 15 planes, in all 3-dimensional plane. Okay, so the father of finite geometry's role. So, his expository memory on continuous groups and geometric classification published in Encyclopedia der Mathematische Wissenschaft. So, Fano's contributions to life theory are described by Armand Borel in his historical essay on Lie groups. So, he wrote a book with the subtitle Geometric Introduction to General Relativity that connects geometry and physics. So, in 1892, a famous model projective plane named today the Fano plane is in particular constructed. So, Fano originally studied a 3-dimensional geometry, but a cross-section formed by a plane passing through his configuration yielded a plane finite geometry. Okay, so finite geometry of Fano has 5 axioms. So, first, axiom 1. So, there exists at least one line. Okay, so A and C is one line. Exists at least one line. So, axiom 2, every line of the geometry has exactly 3 points on it. So, every line of the geometry has exactly points. So, D, E, F. So, points D, E, F has exactly 3 points. So, not all points of the geometry are on the same line. So, not all points are on the... So, points D are not the same line on A, B, and C. So, axiom 4, 4 distinct points, there exists only one line on both of them. So, point D, E are joining points with A, G, F, A, B, C, and E, B, F. So, axiom 5, each 2 lines has at least 1 point in common. So, each 2 lines has at least 1 point in common. So, A, B, C has a common of point B. So, next is the theorems. So, each 2 lines have exactly 1 point in common. So, taken from axiom 5. So, similar ni siya sa axiom 5, which is kanang naa siya kanang exactly 1 point in common, like A and C has exactly 1 point of B. Next is the Fano's geometry consists of exactly 7 points and 7 lines. Okay, so let's see if kanang 7 points and 7 lines of the finite geometry. So 1, point 1, 2, 3, 4, 5, 6, 7. Okay, 7 points. And then 7 lines is line DA, 1, 2, 3, 4, 5, 6, 7. So let us proceed to the last topic, which is the finite geometry of Young. So before we explore the axiom and theorem of Young, we first should know him. So Young born in 1773 in Somerset, England, and he is very intelligent child, learning to read at age 2. So he studied medicine in London and became a physician on 1793. He moved on to studying light, introduced the original theory of color. In 1816, he helped ascertain the precise length of the secant or secant pendulum. So one of the first to try disappearing Egyptian hieroglyphs by studying the Rosetta Stone. So he first defined energy in scientific terms. His description of elasticity came to be known as Young modulus. And also, he established a finite geometry. So what is finite geometry of Young? So finite geometry of Young is different of Fano. So Young obtained the geometry from Fano, then he modified the last axiom. So has the first 4 axioms of Fano's geometry along with the substitute axiom for axiom 5. So this finite geometry is a finite geometry of 9 points and 12 lines. So next, so let's proceed to the axioms of Young's geometry. So I have here an illustration. So first, there exists at least one line. So in the illustration, there exists at least one line. So the line ABC or CFI, then etc. Then axiom 2, every line of the geometry has exactly 3 points on it. So example, line ABC, so now it has 3 points, the point A, point B, and point C. So axiom 3, not all points of the geometry are on the same line. So not all points on the geometry are the same line. Just and ang line ABC, then the point B is not on the line ABC. So the axiom 4, for 2 distinct points, there exists only one line on both of them. So the two distinct points is the point E and point B. Then the one line that exists is the line B, E, H, and so on. So last axiom, axiom 5, if a point does not lie on a given line, then there exists exactly one line on that point that does not intersect the given line. So that are all the axioms of Young's geometry. So let's proceed to the theorem of Young geometry. So first is for every point there is a line not on the point. So for every point, so example for every point is there is a line not on the point. So there point E, so the line DEF is not on the point E. So next is number 2, for every point there are exactly 4 lines on the point. So point A, there na ay line ADQ, ABC, and EI, and EFH. So for every point, there are exactly 4 lines on that point. So number 3, each line is parallel to exactly 2 lines. So if line ABC is parallel to DEF and QHI and so on, then theorem 4, there are exactly 12 lines. So in Young geometry, there are exactly 12 lines. The line ABC, the line DEF, line QHI, line AFH, and line BDI, line HDC, and BFQ, AEI, and CEQ. So the last theorem of Young geometry is there are exactly 9 points. So the 9 points is point A, point B, point C, point B, point A, point F, point Q, and point H, and point I. So that's all. Thank you.